just adjust this here. You can see me. All right. Thank you. I'm Yash, and I'll be talking today about simulation in sim-to-real for robotic assembly. Okay, first, for those who are newer to the research area, I'd like to discuss the motivation. Why focus on robotic assembly? On the one hand, assembly is ubiquitous. Assembly processes are found in automotive, aerospace, and electronics industries. These processes include fundamental manipulation operations, such as peg insertion, connector insertion, fastener mating, and wire processing. On the other hand, robotic assembly is a long-standing challenge. Industry standard methods can achieve high precision, accuracy, and reliability, but often have high setup and cycle times, require expensive equipment and fixtures, and are sensitive to variation. Thankfully, NIST has actually brought much more attention to this problem by creating the NIST Assembly Task Board benchmarks, as well as supporting annual competitions. Now, why use simulation to solve this problem? Simulation has actually been used for decades to test and optimize safety-critical designs and algorithms in numerous industries. In robotics research, it has also been used to develop planning and control policies through reinforcement learning, or RL. Nevertheless, simulation has not significantly impacted robotic assembly. Most prior efforts to solve NIST-style assembly tasks have focused on development in the real world alone. These approaches are extremely powerful. However, they typically require substantial human effort through mechanical design, trajectory planning, demonstrations, corrections, or resets. Furthermore, they can be difficult to scale to a broader range of assembly problems. We take a simulation-first approach due to its long-term potential to leverage large-scale compute with a reduced need for these human inputs. In this talk, I'd like to tell a mostly visual story of our efforts at NVIDIA in simulation and sim-to-real for robotic assembly. First, simulation. How do you accurately and efficiently simulate contact-rich interactions? Second, learning. How can you use a simulator to train robots to perform assembly tasks? And third, sim-to-real. How can you reliably transfer these simulated behaviors to the real world? I'll be discussing these topics through the lens of two papers. The first is called Factory from last year's RSS, which focused on simulation and sim-based RL for assembly. And the second is called Industrial from this year's RSS, which focuses on sim-based RL and sim-to-real transfer. And the first author of that paper was helping us debug this screen sharing issue. All right, let's start with the first topic, simulation. How can you accurately and efficiently simulate contact-rich interactions? Our key strategies for doing this are based on signed distance field, or SDF-based collisions, contact reduction, and a Gauss-Seidel solver. I'll now go into more detail on each of these topics. To some extent, you might wonder, can't we simulate contact-rich interactions already? We certainly can, but there are limitations. Consider the canonical problem of simulating a nut and bolt. Despite the ubiquity of threaded fasteners across the entire world, it was previously not possible to simulate them faster than real time. There are finite clearances between the threads of the nut and the bolt, which can allow the nut to move with 6 degrees of freedom. Furthermore, accurate triangular meshes of the nut and bolt may consist of over 50,000 elements. It's a major computational challenge to detect collisions between these meshes, generate contact points and normals, and solve non-penetration constraints. As a result, the fastest general-purpose simulators could only simulate a nut and bolt between 1/80th and 1/20th of real time. When starting on this problem, we evaluated several geometric representations that could be used for highly detailed objects. For example, for a bolt, a convex hull clearly doesn't accurately describe its geometry. Convex decompositions may appear to faithfully describe geometry, but close-up inspection reveals spatial artifacts. Even for perfect decompositions, collision checks are expensive and undesirable contact normals can be generated. Triangular meshes can faithfully describe geometry. However, collision checks are again expensive and interpenetrations between objects can be difficult to resolve. Rather than just using triangular meshes, our first key strategy is to represent objects as signed distance fields, or SDFs. An SDF is a map from a point in space to its distance to the surface of an object. For example, this horseshoe here. We pre-compute the SDF values for a particular object A on a dense voxel grid. When object A is approached by a second object B, for example, a second horseshoe, we query the SDF values for object A at points on object B in order to generate contacts. Here we show a mesh-based visualization of an SDF of an M4 bolt. Using SDFs, we were finally able to simulate a nut and bolt interaction in real time. However, for applications in reinforcement learning, we might actually want to simulate hundreds or thousands of contact-rich interactions in real time. For this purpose, we need to further speed up. Collisions between an M4 nut and bolt might generate 16,000 contacts, as you see in this porcupine-like figure here. Due to memory bandwidth requirements, an inherently parallel Jacobi solver would only be able to simulate 20 nuts and bolts on a state-of-the-art GPU. Although it converges faster, an inherently serial Gauss-Seidel solver would be undesirably slow. An important realization is that you don't need 16,000 contacts for accurate physics. Thus, our second key strategy is reducing the number of contacts in a physically grounded way. Our strategy consists of 3 general steps. First, we use SDFs to generate contacts, as described earlier. Second, we assign new contacts to existing contact patches based on how similar their normals are. And third, for any unassigned contacts, we select the deepest ones and create new contact patches. Using this scheme, we can reduce 16,000 contacts to just 300. With a Jacobi solver, we can simulate 1,100 nuts and bolts in parallel. Moreover, a Gauss-Seidel solver is now feasible, and we can simulate a theoretical maximum of 35,000 nuts and bolts. All right, now let's see what these previous techniques can do. First, we can now simulate 1024 M16 nuts and bolts in parallel environments in real time, which is a 20,000 times speed up over the state-of-the-art in a general purpose simulator. Next, we can simulate more complicated scenes involving robotic manipulation. In this scene, nuts are placed onto a plate vibrating at 60 Hertz, and a Franca robot executes a hand-scripted trajectory to grasp a nut, pick it up, and move it to the bolt and tighten it. We can simulate 128 parallel instances of this environment in real time. Finally, I feel obligated to show this example. We can simulate all rigid components of the first NIST board, including gears, BNC connectors, including the spring-back mechanism there, D-subminiature connectors, as well as Ethernet and USB connectors. And I can definitely address any questions at the end of the talk. All right, let's move on to the next topic, simulation-based learning. How can you use a simulator to train virtual robots to perform assembly tasks? Our key strategies for doing so are building training environments for robotic assembly, using model-free RL algorithms and decomposing long horizon tasks into subtasks, and performing a systematic exploration of observations, actions, and rewards. I'll go into more detail on these topics now. We built 3 virtual environments for robotic assembly. For each of these environments, we carefully designed or sourced geometric models based on the NIST assembly boards. The nut and bolt environment contains a Franca robot and disassembled nuts and bolts. The default goal is to pick up a nut, transport it to a bolt, and tighten it to the bottom. The insertion environment contains round pegs and holes, rectangular pegs and holes, and various electrical connectors. The default goal is to pick up a peg or a plug and insert it into the corresponding hole or socket. The gears environment contains a NIST gear assembly. The default goal is to pick up each gear, insert it into its corresponding shaft, and rotate it into alignment. The environments are all available in NVIDIA's Isaac Gym software, and they've been tested up to 128 parallel instances. After building the environments, we of course wanted to show that they were useful for simulation-based learning. We focused on solving one of the most difficult and long horizon of the tasks, nut and bolt assembly, with established algorithms in model-free on-policy RL. Our initial efforts to solve the task end-to-end were not successful. Thus, we decomposed the task into 3 simpler subtasks. Pick, where the robot must grasp the nut from a random location on the work surface. place, where the robot must transport the nut to the top of the bolt, and screw, where the robot must bring the nut into contact with the bolt, engage the threads, and tighten it. We learn a policy for each subtask and then execute them in sequence. Of the 3 subtasks, the screw subtask was by far the most challenging to train. Threading a nut onto a bolt is so natural for us as humans that it may be difficult to understand why a virtual robot trained with RL would actually struggle with it. So here's what our initial results look like. There were sudden collisions between the nut and the bolt, misalignment of the nut when engaging the bolt threads, jamming of the nut during tightening, and precession of the gripper around the bolt. To address these challenges, we systematically explored our Markov decision process formulation for the RL problem. For example, for our observation space, we considered positions and velocities of the robot and objects. For actions, we looked at 2-dimensional versus 6-dimensional post targets, for example. For controllers, we tried operational space and impedance controllers. For gains, we performed a sweep of gain values. And for rewards, we evaluated pose-based distance metrics, key point-based metrics, and so on. Ultimately, our best performing configuration achieved an 86% success rate. Perhaps more importantly, the simulator was stable during the wide range of interactions during training. We then chained together the policies we trained for our pick, place, and screw subtasks to solve the nut and bolt assembly problem end to end. We achieved a 74% success rate, which served as a proof of concept that it was possible for a robot to learn such a task within a physics simulator from scratch. All right, let's proceed to the third section of the talk, sim-to-real transfer. How can you transfer behaviors learned in simulation to real-world robots? Our key strategies for doing so are 4 simple algorithms that we've developed, including simulation-aware policy updates, or SAPU, and policy-level action integrators, or PLAI. I'll provide a bit of context and then go into more detail on each of these. Before I begin, I'll describe our real-world hardware and task definition. We have a Franca Panda robot with a wrist-mounted RealSense D435 camera. Below the robot is a small optical breadboard used for placing or mounting components. Although we previously learned policies for nut and bolt assembly in our simulator, we started our sim-to-real effort with insertion-style tasks, as we believe these to be a bit less complex. We designed peg and hole assemblies on the left, 2-prong and 3-prong electrical connector assemblies on the top right, and a 3-gear assembly closely adapted from the NIST boards. I'll use the term plugs to generically refer to all the pegs, connectors, and gears, and the term sockets to refer to all the mating components. Our fundamental task is to assemble all the plugs into their corresponding sockets. As with the nut and bolt problem, we decompose this task into simpler subtasks. First, perception, which entails detecting each plug and estimating its x, y, and theta coordinates on the work surface. Second, grasping, which entails moving to each plug and executing a stable grasp. Third, transport, which entails moving each plug to its corresponding socket and aligning it. And fourth, insertion, which entails inserting each plug or gear into its socket. For perception, we trained an object detection model based on mask RCNN, and for grasp, transport, and insert, we trained RL policies using PPO. And that was the insertion phase. We first aimed to solve these problems in simulation and then transfer learned policies to the real world. Needless to say, this didn't work right out of the box. Some of our earliest challenges were due to major discrepancies between assumptions in our simulator and the constraints of our real-world robot. Specifically, in our original simulation work, we used operational space control, proportional gains around 10 in magnitude, and damping that was heuristically applied to our robot's motion. In the real world, we used a task space impedance controller as we didn't have access to an accurate robot dynamics model. We used proportional gains around 1,000, and although we had damped behavior, experiments suggested that damping coefficients were far less than simulated values. When we brought these real-world constraints and parameters into our simulator, our policies all began to fail, which motivated the development of our algorithms. Our first and most critical algorithm for simulation-based training is the simulation-aware policy update. Nearly all contact-rich simulators experience non-zero error, which often manifests as small amounts of interpenetration or overlap between objects. Here you see a histogram of interpenetration in our simulator during a typical training episode. Our realization was that it can be helpful to make the policy update process aware of simulator error. Conceptually, for each episode, we compute the maximum interpenetration distance between objects. We then apply a filter to fully discard the episodes for which this value is greater than a certain threshold. For the non-discarded episodes, we weight the return to penalize higher interpenetration distances. I'll also briefly mention two additional algorithms for simulation-based training that we developed. The first is the SDF-based dense reward. This method uses SDFs described earlier to compute how aligned or misaligned an object is with its target pose. The second is a sampling-based curriculum. The translucent object shown here is the mesh of a socket, and the yellow spheres designate randomized initial locations of a peg at progressive stages of training. The problem is easiest when the peg begins partially inside the socket, and is hardest when the peg begins fully outside the socket. In the sampling-based curriculum, we ask the robot to solve the hard version of the problem even during initial stages of training, which prevents overfitting to the easy problem. However, we make the distribution more and more difficult over time. We evaluated the previous algorithms through ablation studies over a total of 265,000 simulated trials. As our final set of evaluations, we deployed all three algorithms at the same time and trained under various levels of initial state randomization and observation noise. For moderate levels of randomization and noise, we achieved an 89% success rate for peg and hole tasks and an 85% success rate for gear assembly tasks. With no randomization and noise, performance was nearly perfect. Although we brought real-world constraints into simulation and developed algorithms to train simulated policies successfully, that still wasn't enough for sim-to-real transfer. One critical remaining issue was steady-state error in the real world. To visualize this point, here's a policy trained using the previous algorithms to move its fingertips to the pink sphere. On the left, the robot is imperfect gravity compensation, and on the right, the robot is unmodeled joint friction. And as you can see, the robot never quite reaches its target, which is an issue that also occurred in the real world. To address steady-state error, we developed a fourth and final algorithm, the Policy Level Action Integrator, or PLAI. This algorithm was used exclusively for real-world deployment of our policies. An established RL approach for robotic manipulation is to interpret actions as delta state updates. The desired state is the current state composed with these actions. Instead, PLAI applies actions to the previous desired state. If this step is not intuitive, it's actually mathematically equivalent to saying that your desired state is your initial state plus the sum of all actions over time. And thus PLAI acts as an integrator over policy actions. Here's a comparison of the standard approach shown previously with classical PID control in our PLAI algorithm. In such a scenario, PLAI has consistently lower steady-state error. We repeated this experiment in the real world and achieved extremely similar results with a mean steady-state error of approximately 2 millimeters, which is quite low for our given robot hardware. In summary, PLAI is a simple but highly effective means to minimize error with respect to policy targets. With our 4 algorithms, we now had the tools in place to finally succeed at sim-to-real transfer. For the rest of this part of the talk, I'll show videos of us deploying simulation-trained RL policies on our real-world system. Before I do so, I just want to recap that these are the 4 subtasks we focused on: perception, grasping, transport, and insertion. We evaluated our ability to perform these subtasks through a series of experiments across 600 real-world trials. Here's an experiment that coupled our perception module with our transport policy to assess how accurately our policies could achieve pose targets in the real world. Specifically, we placed sockets at random locations and orientations on the breadboard and placed bullseye targets on top of each socket. We grasped a laser pointer, detected the sockets from RGB images, and measured how close the laser was to the bullseye. The system achieved a mean steady-state error of 4.2 millimeters over all trials. Here's an experiment that coupled our perception module with our grasp policy and our transport policy to assess whether we could perform a simple sortation task. Specifically, we placed various pegs and gears at random locations and orientations on the breadboard, and we placed small orange bins labeled with part categories in front of the breadboard. We then detected all parts from RGB images and deployed our grasping and transport policy on each part. The system was able to sort all the parts into their corresponding bins with near perfect success rates quite repeatably. And here's an experiment that evaluated our insertion policies in isolation. Specifically, we bolted sockets to randomized locations on the breadboard. We placed a part into the gripper, guided the part into its corresponding socket, and recorded the location of the gripper as a target pose. We then randomized the location of the gripper and plug above the socket, manually applied observation noise, and then executed these policies. Our system achieved success rates of 83% over all trials. For high randomization and observation noise, the policies often exhibited searching behavior, which was also observed in simulation. The 2-prong and 3-prong connectors, as well as the small and large gears, were actually never seen during training. Finally, here's an experiment that coupled our perception module with our grasping, transport, and insertion policies to assess whether we could perform end-to-end assembly tasks. Specifically, we placed various pegs and holes, connectors and receptacles, and gear shafts at random locations on the breadboard. We then detected all parts from RGB, deployed our grasping, transport, and insertion policies on each part, and the system was able to assemble plugs into their corresponding sockets with an 89% success rate over all trials. Near perfect success rates were achieved on the gears and connectors. To our knowledge, this is the first system to demonstrate RL-based sim-to-real transfer for end-to-end assembly without a dedicated policy adaptation phase in the real world. Okay, we've covered a lot of ground, and I'd like to finish with some concluding thoughts. What are the takeaways, what's in progress, and what are the next steps? So let's start with the takeaway points. Where are we now? What I've hoped to show in this talk is that we can now simulate contact-rich interactions often 100 to 1,000 times faster than real time. We can use this fast simulator to learn RL policies for robotic assembly, including with data-hungry but powerful methods such as model-free on-policy RL, and without the use of human demonstrations. And we can transfer simulated RL policies to the real world without human corrections or a policy adaptation phase. What are we working on now? I'll provide a quick preview here. We're actively working on several directions. Two recent ones that might be of interest include sim-to-real transfer for assembling nuts and bolts, which was the original task that motivated us, as well as other threaded fasteners, and fast tactile simulation, which can enable policies that are highly robust to object perturbations before or during contact. Finally, let's discuss next steps. What are the most important challenges ahead? From my view, there are three key problems at the front of the queue. How can we achieve 99% or higher success rates, which is often expected in industry? How can we solve harder problems with sim-to-real transfer, such as some of the deformable assemblies on the NIST boards? And we've shown solutions to approximately 10 assembly problems with sim-to-real. How can we increase this by an order of magnitude? And my long-term hope and vision is that one day, every advanced industrial robot will be trained in simulation, allowing it to truly scale. For those of you who are interested in trying our simulation tools or reproducing our real-world results, feel free to take a photo or a screenshot. Our simulation tools are available in 2 repos, and our sim-to-real tools, which include CAD models, industrial kit, algorithm implementations, industrial sim, and real-world policy deployment code, industrial lib, are all planned to be released within a month's time. Last but not least, the work that I described today has been a multi-team effort at NVIDIA with deep contributions from experts across both simulation and robotics. I'd like to highlight 2 people in blue, Bingjie Tang and Michael Lin, who are NVIDIA interns and the authors of the sim-to-real paper, Industrial, that we're presenting this week. Bingjie is here in person, of course, and we'll be presenting the work on Wednesday, so please stop by. Thanks for your time. I really look forward to seeing your results ahead, and I'm happy to answer any questions.
Hey, Yash, thanks for the talk and nice to see you here.
Nice to see you again, yeah.
I have a question about the first part. You talk
sure.
about the physics simulation based on SDF.
Yeah.
I'm wondering, do you need to change the physics simulator like parameters, or you just need to change the contact modeling from SDF to, or from the traditional mesh to SDF? Then the physics simulator will just remain the same.
Yeah, the good thing is that, I guess I didn't show it in this presentation, but there's usually very little tuning required for using this new contact formulation, the way that we've kind of set it up. So basically, one prerequisite is that you have high quality meshes. So if your meshes are, for example, poorly tessellated, you'd want to basically achieve fairly high element density in the mesh itself. And then basically what the simulator does is it will take the mesh's input and generate an SDF from it. And when it generates an SDF, there's basically only one parameter that you might typically tune, which is essentially the voxel density of the SDF. But for pretty much every example that you've seen in this presentation, it's actually been the same value. So really not much tuning required there. Okay, great, yeah.
So Minas posted a couple of questions. Minas, would you like to just unmute and maybe ask them yourself?
Yeah, I wanted to ask, what about more complex interactions, contact-rich interactions with everyday life objects or assembly components or tools? How do you address the challenge of accurate simulation of soft contact models, frictions, slipping, and uncontrolled rolling? Because typically when we do complex tasks, we have uncontrolled slipping and rolling. And what about the time overhead for developing the simulation? Can you give us some comments on the time and cost overheads of developing simulation solutions?
Sure. So let's start with more complicated objects. So I think the examples that you've seen here predominantly were all rigid body assemblies. There were a couple of exceptions to that, and that was actually in that sort of NIST board demonstration, where we were able to actually simulate, for example, the deformation of the tab on an Ethernet connector and the deformation of the metal pins that are inside the waterproof connector. But for everything you've seen here, it's been rigid body. So that's really a fundamental constraint right now. We're very actively working on merging our work with deformable body simulation. There are actually quite a number of people working on soft body simulation at NVIDIA. So we're trying to merge these two efforts. But right now it's really limited to rigid body assemblies. We do observe, fairly accurate, at least qualitatively, simulation of phenomenon like slip and rolling. So I think that much is there, but soft body is still very much in the works in terms of making it ready for any user to go ahead and use. The second thing is on I think the second question was on sort of the time and development cost. It would be hard for me to come up with a complete estimate of that off the top of my head, but in terms of how long have we been working on this, I started working on this in the middle of 2020, and the first effort was on the simulation side, and at that point in time, working with one other person primarily, Miles Macklin, in early and mid 2021. As the project grew, other people started getting involved. As of, let's say, 2022, there have been about, let's say, between 3 and 6 people kind of working on this, but not necessarily full time. So it's been a multi-year effort and definitely multi-person effort. But hopefully by sort of showing the initial steps, it can kind of reduce any development costs in the future. And I'm not sure if your question was also regarding sort of time required to actually train these policies, but in case that's also of interest, each of these policies typically took between 1 and 1.5 hours to train in that early simulation work. And some of the policies in the sim to real work took a bit longer because of the way we were implementing those sort of 4 algorithms. But we've been recently accelerating that using a library called Warp, developed by NVIDIA. And hopefully that time should actually come down again to the few hour range.
Great, thank you so much. And one more question. Did I hear a 4.2 millimeters error?
Yeah, so that was
correct?
that's a good question. So for specifically reach tasks with the robot, we were able to achieve about 2 millimeters of error. And when we were actually running experiments for the paper, and we actually were doing this laser pointer experiment, which not only had any error that was due to control or due to our policy, but also error due to perception. That combined was 4.2 millimeters, sort of in misalignment error. That being said, one asterisk is that during the development process, we unintentionally were deploying stochastic policies. Now, as you can imagine, that definitely makes it definitely can introduce a bit more error when it comes to actually, reaching a location and steadily targeting that location. So when we actually deployed with deterministic policies, our results, significantly improved. But we didn't do a very rigorous quantification of that, so I didn't want to present that number.
Okay, thank you so much.
Thank you.
All right.